Alright gang, here we go. This is for Chem 2 Unit 11. We're talking about acids and bases. This beginning video here should be pretty review. We talked a fair amount about acids and bases several units ago when we talked about aqueous solutions. And now we're going to really deep dive into acid-base chemistry because it's really important. Now, one thing that you need to know about acid-base chemistry is our collective humanity's knowledge of acids and bases has been around for several thousands of years. The Greek philosophers would encounter acids and they would qualify them or identify them based on their characteristics. Primarily, do they taste acids tasted sour and bases tasted bitter? Acids would react with certain metals to form like bubbles. They didn't know it was hydrogen gas, but it is. And bases and acids would neutralize each other, so on and so forth. And so acids and bases, like as themselves, have we've known about them for a long time. And so this first couple of slides here, we're gonna talk about two prevalent definitions of acids and bases. These are probably review from your previous chemistry courses, so we'll go through them really fast. If you need more of a refresher, check out my Chem 1 series when I talk about acids and bases. So the very first definition that defined what an acid was, based more than just on its properties, was this guy named Arrhenius. And this is the same Arrhenius that came up with the Arrhenius equation that we talked about when we talked about kinetics. Remember, his equation allowed us to use kinetics and K value in order to find the activation energy of a reaction, right? So anyway, he defined that an acid is a substance that when you put it in water increases the concentration of hydrogen ions. So it makes the hydrogen ions go up, all right? So you could just say it increases H+. All right, concentration of H+. All right, and then a base is a substance that when dissolved in water increases the concentration of hydroxide ions. All right, so we could really say that this guy increases the concentration of OH minus. All right, now this is all fine and dandy, but the problem was that there were several compounds and several molecules that we encountered that acted like acids. They tasted sour, they reacted with metals, they neutralized bases, so on and so forth, but they didn't fit this model. Okay, and so the race was on to establish another definition of acid-base chemistry, and then along came Bronsted-Lowry, and then the third one that we'll talk about later. I'm sure you chemists that are knowledgeable probably wonder, well, where's Lewis? We'll talk about that one later, but we're going to focus on Bronsted-Lowry definition because it's a little bit more robust, and everything that's a Bronsted-Lowry acid is also an Arrhenius acid. Or anything that's an Arrhenius acid is also a Bronsted-Lowry acid, but not everything that's in a Bronsted-Lowry acid is defined as an Arrhenius acid. So this Bronsted-Lowry definition is a little bit more robust, and this is pretty easy. Anything that's an acid is defined as a proton donor. All right, so essentially when we say proton, we really mean it's giving up that H+, okay? And then a base is anything that's a proton acceptor. All right, so acids are proton donors, bases are proton acceptors. So let's look at water, what it does when it's a proton acceptor. So remember, proton acceptor means that it's a base, all right, by Bronsted-Lowry definition. It says when a hydrogen ion is formed in water, it does not exist alone for long. Okay, and so what they're showing you here is if you put an acid in here that produces this H+ ion, it's not going to stick around like this many thousandths of a tenths of a second, and then it's just going to be bonded to a water molecule. And so this water molecule will act like a base. It'll act like an hydrogen acceptor, okay, or a proton acceptor, and then it forms this guy. And you should recognize this. This is our hydronium ion, polyatomic ion that we've looked at before. And so you should realize really the fact that we talk about it being a proton acceptor, whenever we're talking about this H+, really we're talking about hydronium. So the actual correct way to represent an H+ would be like a hydronium, would be that H3O+, because that's what we're making. Because this really H+ does not last very long. All right, and so here you've got this ball 3D representation ball model of what this looks like. You got your Lewis dot structure of what it looks like, so on and so forth. All right. Now, a Bronsted-Lowry acid must have at least one removable acidic proton. okay, must have, and that makes sense because it has to be a proton donor, okay, and if it's a donor, that means it has to have something to give away. The Goodwill would not look at me very kindly if I showed up and says, I have a couch to give away, and they look in my car and there's no couch in there, and I'm like, oh, never mind, I don't have a couch to give away, but I have one to give away. You know, it doesn't make sense. So Bronsted-Lowry acid must have the removable acidic proton. Okay, and then a Bronsted-Lowry base must have at least one non-bonding pair of electrons to accept that proton. All right, so you know, if I show up with that couch and then and Goodwill doesn't have a spot to put a couch, then they very well can't act like the acceptor. They can't be my base to my couch. Okay, and so here you've got hydrochloric acid and water, and then it's this hydrogen chloride is turning into, or this hydrochloric acid is turning into a chloride ion, right? We're always going to follow the anion, okay? And then this water is turning in hydronium, all right? And so you can kind of follow what turned into what on one side of the equation. And that's really the first step in analyzing these equations, is following these anions. So this chloride goes from here to here, and the oxygen goes from here to here. We can see that the chlorine loses a hydrogen and the oxygen gains a hydrogen, okay? And so here's, you know, just different representations of that same thing. Now, the interesting thing about water is that water is what's called amphiprotic. All right, amphiprotic means that it can either donate a proton, it has the ability to donate a proton, or it has the ability to accept a proton. All right, so here your water molecule accepted a proton, right? It acted like a base. And then, oh, they have it labeled down here, cool. And then it acted like a base and turned into this, and then the hydrochloric acid acted like an acid. It gave up that hydrogen. Here, when you put the water with a base, like ammonia, you know, we can follow the anion, so our nitrogen goes from here to here, and we can see that from here to here, it gains a hydrogen, so that means our ammonia acted like the base, and then our water, we can follow that oxygen, goes from here to here, and we can see that this oxygen lost a hydrogen, so that means it acted like an acid. So over here, our water acted like a base, and here it's acting like an acid, and really that's what, you know, this is a good example of an amphiprotic molecule. It's just something that has the ability to accept or donate a proton. All right. Now, in Bronsted-Lowry acid bases, whenever we form this reaction, the two formulas that are differed by that H plus are called conjugate acid-base pair. All right, so in this example, our ammonia turned into ammonium. They're different by one hydrogen. Okay, see there's an NH3 versus NH4. These are a conjugate acid-base pair. And then water with the hydroxide, again, they're different by one hydrogen. They're an acid-base pair. All right, so here they're given this reaction here of nitrous acid with water. The nitrous acid, again, follow the anion, so that's your NO2, goes to the NO2 minus, right? And it's losing this hydrogen, so this means that this guy in pink here is a conjugate acid-base pair. All right, and then in the blue, the hot water goes from H2O to H3O plus. Again, it acts like a base because it's accepting a hydrogen, and it's paired up with the hydronium because they're only different by one hydrogen. Now, you might be asking yourself, well, why do we call it a conjugate base on this side if it was an acid on this side? You have to remember last unit we talked all about equilibrium. We talked about how these reactions can go in reverse order, right? And really, there's no difference. They can go forward or backwards. Doesn't really matter. And so this nitrous acid, if we look at it, well, from here to here, as we go across, the NO2 is losing a hydrogen, so it's acting like a base, or an acid, excuse me. But when we follow it, go in the opposite direction, this NO2 minus is accepting a hydrogen, right? If we, you know, it was losing a hydrogen in the forward reaction, but in the reverse reaction, it's accepting a hydrogen. So if it accepts that hydrogen in the reverse reaction, that means it's acting like a base in the reverse reaction. So that's why we call it a base. And then we put that conjugate in front of it because that means it's on the reverse reaction. So the acid will always go with the conjugate base. Okay, and then what happens with the base? Well, the base in the forward reaction is obviously accepting the hydrogen. It goes from H2 to H3, right? It accepts that hydrogen as it goes, and that's why it's a base. But if we follow the hydronium in the reverse reaction, it goes from H3 to H2, and so it's lost a hydrogen. Okay, and because it's lost a hydrogen, it's acting like an acid. Okay, and so we call it the conjugate acid. So the base will always go with the conjugate acid. All right, and so we form these acid-base pairs where we've got the acid going to the conjugate base and the base going to the conjugate acid. All right. All right, let's try this guy. It says, write the formula for the conjugate acid of each of the following. All right, so we'll write one out the long way, and then you'll see the pattern is pretty easy. So if you have HSO3 minus, and we add this with water, it doesn't really matter what we add it to. Now it says that it's we want to write the formula for the conjugate acid of this guy. So that means we need it to act like a base, which means we need the water to act like an acid. Okay, and so if it's going to act like a base, that means it's going to accept a hydrogen, so it'll turn into H2SO3, and then the water will act like an acid, so it'll turn into OH minus. All right, so this here, that's the formula for the conjugate acid, and we know it's the conjugate acid because it's came from the base in the forward reaction. We could also look at it in the reverse reaction. It's losing a hydrogen, and it's acting like an acid, but it's in the reverse reaction, so therefore it's the conjugate. All right, and you can see, like, in order to find the conjugate acid, all we have to do is add a hydrogen to it. We could write out this formula, but we don't need to. It didn't ask for it. It just asked to write the formula. So for fluorine, we just add a hydrogen to it, so it would just be HF, and then we add a hydrogen to phosphate there. It'd be HPO4 2 minus, and then we have HCO plus. Notice that the charge goes up 1 because we've added that extra proton. All right. It says write equations for the proton transfer reaction. So it says lithium oxide Li2O is dissolved in water, and so since it's dissolved, we know it's going to turn into these ions. So it's going to turn into 2 Li pluses and plus 1 oxide. All right, and then it says the solution turns basic from the reaction of the oxide ions with water. Write the equation for this reaction and identify the conjugate acid-base pair. So the lithium ion isn't participating in the reaction. We know that because the oxide ion is right. It just talks about the oxide ion. So we put O2 minus, and it's going to react with our water. Okay, and it's in equilibrium. All right, and so let's see. Well, this is going to act like a base because it does not have an acidic proton to give away. So that means our water has to act like the acid. So this means this guy has to accept the hydrogen. So it's going to look like that. And then this guy's going to lose a hydrogen. So it's going to look like this. All right. Well, you should be able to tell that it's making both of these. This is part of the reason it's so dang basic, is because it's making 2 hydroxides instead of just 1. All right. And so the base turned into this guy here. So that means this is the conjugate acid, okay, because then the bases go with the conjugate acid, and that means this would be your conjugate base because it came from the acid. Not too bad. All right, last little bit here. We're going to look at this chart here, and let's look at this chart real quick. So here's the chart, and you've got increasing acidic strength here and increasing base strength here. So notice they're in opposite directions, and you'll see across, if you go straight across, it's lining up the acid with the conjugate base, or the base with its conjugate acid. All right, and so HCl, its conjugate base would be Cl minus, right? And so they've got the strong acids here, these top 3, and the strong bases down here, these bottom 3. All right, and so remember back in way back in a couple units ago, we memorized those strong acids, and so you need to make sure you have those memorized as well. There's 7 of them, right? Your strong acids. All right, so let's see if we can remember the saying here. 5, 6, 7. All right, so you got HI, so your high chlorine and bromine. There's 3,344 of you. 2 of you are ClO. Are the other 2? No. You're something else. And then we add our hydrogens. So we got HI, HCl, HBr, HNO3, HClO3, HClO4, and H2SO4. Nailed it. So those are your strong acids. And then you have your strong bases. And your strong bases are these guys here. So we've added, oops, down here. I was like, those aren't strong bases. These guys here, these 3 here, and then any of the alkali metals with OH minus, or alkaline earths with OH minus, except magnesium. Poor magnesium. All right. So anyway, but based off, so that's just something to remind yourself of from before. But we've got this list here Okay, strong acids, strong bases down here. Notice that the strong acids, their conjugate bases are negligible basics. Essentially, they're just neutral. They don't do anything to the basicity of your solution. And then the same thing on the strong bases, that the acids are negligible acidic. All right, so, and then in the middle, you got weak and weak. Okay, notice here that you've got water here on the acid side and water here on the basic side. All right, so then it says acids above the line with H2O as a base are strong acids. So here's our H2O as a base. These are our strong acids. Okay, their conjugate bases do not act acids as water. Okay, that makes sense. All right, bases below the line, okay, are strong bases. Their conjugate acids do not act as acids in water. So here's H2O as an acid. These are our strong bases, and we can compare them. Their strengths going the other way. All right, so in every acid-base reaction, we're going to have to decide which side we favor, okay? And it's always going to favor the transfer of the proton from the stronger acid to the stronger base, okay? So essentially, in order to figure out which side of the reaction is favored, what you need to do is compare, okay, compare the acid strength, all right? For now, we're just going to have to do it using that chart, but here pretty soon we'll learn a couple other tricks to allow us to do it a little bit differently without relying on a chart. So for example, this guy, we've got HCl, and so we're just going to find the two acids. So from this side to this side, okay, this would act like one acid, right? And then from the other way, we've got hydronium, and so this would be our conjugate acid. Right, so we're going to compare the acid with the conjugate acid. So we find HCl is way up here, and then we have H3O plus, which is down here. Notice HCl is stronger. Okay, so it's going to be, we're going to follow the right side. Okay, and they do the same thing but with the base. Okay, they say, so here this would be the base. Okay, and this would be the conjugate base. We can see that ClO minus is a negligible base and H2O is a stronger base. So therefore, it's going to favor going to the right. All right. Now we can do the same thing here. All right. And we've got, so, again, they do it with bases, but we'll practice it with acids because I find that easier just to think about the acids. So from going to right to left, we got to find the acids. So the acetic acid here goes to acetate. So this means this is one acid. And then on the other side, the H3O plus would have to be the conjugate acid. All right. And so now we just got to figure out which side has the stronger acid. It's either H3O plus or acetic acid. Well, acetic acid is just right here, and H3O plus is right here. So H3O plus is a stronger acid than acetic acid. So that means we're going to favor going the other way. So we're going to favor the left-hand side. All right, and they came to the same idea. Here, our K value would be less than 1. Okay, remember our K value, just to recap here, K is equal to the concentration of the products divided by the concentration of the reactants. Okay, so if our reactants have bigger concentration, that means our denominator is bigger and our value would be less than 1. All right. Practice this guy right here. All right, it says based on information in 16.4, place the following equilibria in order from smallest to largest value of Kc. So really for each of these guys, we got to just figure out, well, what would our Kc value be? There's a rogue equilibrium symbol here. I do not know why. All right, whatever. Ignore this. All right, so it says acetic acid with hydrogen sulfide. So what we got to do is just look for the two acids here. So acetic acid would be one acid. Okay, so that'd be one. And then so the other acid would have to be this hydrogen sulfide, H2S. All right, so acetic acid, hydrogen sulfide. We jump back to our chart here. We find acetic acid. He's right here. And we find hydrogen sulfide. He's down here. Acetic acid is a stronger acid. So that means we're going to be pushing away from the acetic acid. So that means this guy will have a equilibrium value greater than 1, but probably not much greater than 1 because it looked like acetic acid wasn't too much stronger than H2S. Granted, we don't really have any values. It's just a relative table, right? All right. Now for the second one here, we've got fluoride with ammonium making hydrofluoric acid and ammonia. All right. So it looks like the ammonium loses that hydrogen as it goes left to right. All right. So there's one acid, and so the conjugate acid would have to be the hydrofluoric acid. All right. So now we just got to compare those two guys. So ammonium and hydrofluoric acid. So we find ammonium's right here, and hydrofluoric acid is up here. All right, so that means that hydrofluoric acid would be the stronger acid, so we'll push away from the hydrofluoric acid. So that means we're going to favor the reactant side. So that means our K value will be less than 1. All right. Now, last one here, we've got carbonic acid. That's obviously our acid because it's got acid in its name, and the hydrochloric acid. Well, this one's easy because we know hydrochloric acid was the highest one on the list. We'll just double check though. Yeah, hydrochloric acid's up on the list up here. Carbonic acid's down here. So we're going to push away from the hydrochloric acid. Not only are we going to push away from the hydrochloric acid, we're going to push away from it a lot. So we'll say like it'll be much smaller than 1. Okay, and so it says in order from smallest to largest values of Kc. Well, smallest would be 3. And then next would be 2, and then 1, so 3, 2, 1, so it's got to be E. All right, so that's just your recap of acids, bases, maybe a couple new things about comparing strengths of acids and bases. Not too hard. Just follow these, if you break it down to simple steps, just look for the acids on both sides, be able to identify which one's your acid and your conjugate acid is really the trick there. So anyway, do practice problems. Let me know if you have any questions, and I'll see you on the flip side.